Okay to go now?
Yeah.
I've got the thumbs up from the YouTube. Thank you very much. Okay, so I will briefly recap. We through NB funding, we've established this International Woodsmoke Researchers Network. We have the website where we will be hosting information, hosting events, and we're posting webinars. And I was also just going to mention the origin of this particular meeting is when we met as a group in July, we felt that technologies was one area that we kind of missed and was deserving of a follow-up meeting. So we reached out across the network and obviously from people we know to have a series of talks just to get everybody up to speed on current and emerging technologies in this area. Now, the format is we've got sort of 15-minute talks, and some of the speakers are in this room here in Auckland and some aren't. So again, fingers crossed and the technology will work fine. This may be a little bit tricky for questions, so I think what we decided to do is try and hold back on questions to the end. So we'll leave a 15-minute session at the end for questions for any of the speakers. All our speakers will be staying for the whole meeting, and we'll see how that goes. If there's any urgent questions, then we'll see if we can squeeze those in. So some basic housekeeping. Because it's a 2-hour meeting, we've decided to go straight through. However, here in the Auckland building, there are toilets just down the corridor on the right. We do have water at the back of the room, and we'll be finishing at 12 o'clock. So at this point, hopefully I'm going to hand over to our first speaker, who isn't here, he's in Christchurch. Richard, are you there?
Yes, I am. Hello.
Excellent. So let's see how this goes. I'm going to hopefully now hand over to Richard, who will appear on our screen here in Auckland. Are we okay, Yushi?
Yes, yep. You see me all right?
Not yet. Do I need to do anything at this end? Yeah, Yushi.
Can you bring up his screen?
What have we got? Just tell me what you got.
Yep, I got your screen.
You've got the graph?
So now if you stop sharing, we should be able to see you.
Right, yeah. Where are we here? Okay. Well, that's all right. I'll just carry on. Did you see the graph when I brought it up? Oh, that's all right. Look, I'll just carry on. I'm not sure what's going on, but we'll get there. Look, I was asked to present a brief presentation on the current low emission burners, and that's a product that's been used for some time now. The very first regulation for what we consider the current low emission burners was introduced by Environment Canterbury in their 2002 air plan. And that was a 1 gram of particulate per kilogram of fuel emission rating and a 65% efficiency rating. That was followed up by a National Environmental Standard regulation in 2005. And that was a little bit higher at 1.5 grams per kilogram and 65% efficiency. Hopefully you guys can see a graph up on screen now.
Yes.
Yes, yep, great, yeah. So this is a fairly widely distributed graph from the Christchurch clean air zone. The ULEBs have been successful at reducing the number of exceedances and concentrations of PM10. So the graph illustrator, which a number of people would have seen before, shows that the black lines are the concentrations of PM10s, and of course our years down the bottom. So if we look at the concentrations, we can see that about the 2002-2003 era, there was a change in the PM10s that were recorded in the Christchurch clean air zone, and there has been a gradual reduction in those emissions and we've continued on a downward trend. At the top of this graph, there is the number of exceedances rather than concentration. You can see in that 1999 era, we had 60 exceedances down to last year of a low of 8. So with the current low emission burners, they have been, we consider them successful at reducing the number of exceedances and also the concentration of PM10s. The construction of the low emission burners, which has enabled them to do this, is they're still a fairly simple device, but there's really two major reasons for the reduction in the PM10s with using the devices. The first is that the construction of the burner physically eliminated the burner from being shut down to a very low setting, and as a result it changed the culture of how people use their wood burners. There was a time when if you had a wood burner, the goal was to basically keep it burning 24 hours a day. So at night time you would load it up and you would shut it down to a virtual smolder, and you'd have these plumes of smoke exiting. So the low emission burners essentially eliminated that option of the smolder. And they also introduced some technology to help obviously clean that up, and that was by increasing the combustion temperatures. Hopefully you can see the next slide. This is one of the current ULEB fires out there that we manufacture. The technology inside that's fairly simple in terms of how it's constructed, but there are two main things to point out there. The first is the refractory lining. In this particular model, the firebox is lined with compressed vermiculite brick. There are other materials that are quite commonly used, which are kilned fire brick and also a promat board. The other feature in this slide is the introduction of secondary air. And the introduction of secondary air introduces oxygen at various points to help complete the combustion process. That's done in a number of ways through either air tubes, baffles, various things like that. Generally, the idea is to introduce it into the gases, into the flame, where it's burning volatiles and wood gas that's been baked off the wood, and that's been fairly effective. LEBs, well, low emission burners, as you saw in the graph, have been really successful in reducing PM10 concentrations, but LEBs are still subject to a number of to misuse and abuse by consumers, and that's something that is really important that the industry has been promoting, which is education for both the wood side and also the use. That's something that's been embraced quite successfully by Nelson and Nelson Regional Council and the Environment Canterbury. Both groups have introduced what they call a Good Wood program, Good Wood campaign, which is essentially getting wood merchants inside to introduce well-seasoned dry wood, which makes a big difference in the combustion. And Environment Canterbury has also been involved heavily in an education process with on an individual and a group basis, educating customers how to light fires and how to burn them properly and how to use them. That has shown to be very effective at controlling PM10s further. A lot of the issues are that because the low emission burners are able to be abused, you do get a certain portion of the population who will misuse them and ruins it for everybody. So through the education process, we have been able to, as an industry, to further increase the effectiveness of low emission burners. And low emission burners are very effective as a low entry point for home heating. Because they are fairly simple construction, and for a particular market, particular demographic, they are actually a very, very important source, and sometimes the only source of heat for them. So keeping wood burners fairly simple in terms of construction is important for achieving those needs, and we can by doubling up with education, we can definitely continue to make a difference. That's really about my presentation. It's a technology that's been out there for a number of years now, and a number of the manufacturers are probably aware of it. We believe it's a very successful formula that is still continuing to reduce emissions in many areas. So that's it for me.
Thank you very much, Richard. Can everyone hear me who is not in Auckland? I think so. Okay. So I apologise, I should have said right at the start, but Richard is representing Harris Home Fires. Is that right, Richard?
That's correct, yeah.
Excellent, thank you. So we're slightly ahead of time, so we'll see here if we can actually take some questions. So first of all, I'm just going to ask if anyone in the room here in Auckland has questions for Richard. Okay.
Thanks for maybe the eruption.
Sorry.
Sorry to interrupt. When did you use microphone?
Microphone at the back of the room, is that right? Great.
That's one.
Yeah.
Hi, can you hear me?
Yes, just, yeah.
I just thought maybe around about 2011 when the earthquake happened, was there a lot less people using the wood burners after that stage?
Sorry, can you just repeat that question?
After the 2011 earthquake, was there a lot less people using the wood burners at that time?
Yeah, well, I mean, there were a lot of people down here in Christchurch where actually all of a sudden many heat sources stopped working. And so around the earthquakes, there was an increase in wood burner use. On the flip side, there were also a lot of brick chimneys, open fires that came down. And so the effect was quite hard to gauge at that stage. But, you know, the wood burners were a very important part of the recovery process after the earthquake. It was obviously to keep people warm, but also a sense of, safety and security as well around those uncertain times.
Yeah.
Hey, Richard, Jeff Floyd here. Hey, just you're a member of the Home Heating Association. I guess my question is, if we're looking at the competition amongst the industry, there's obviously price points, there's design, there's lots of burners. In terms of efficiency and lower emissions, what sort of driver is it in the development amongst the industry? Would you call it a primary or a secondary?
Yeah, well, I think in terms of, obviously it's a primary when you consider hitting the actual, hitting the emissions and efficiency level, because obviously if it's above it, you can't sell it. So that's a primary driver. But in terms of getting down below those numbers further, there is no incentive. If we're talking a 1 gram, 1 gram in, Canterbury, then I've really got very little incentive to get anything below that. But the industry does strive to continue to improve efficiency and those emissions. I mean, it's, once upon a time when those regulations first came in, 1 gram fires were hard. Now it's quite a common occurrence to have fires, that have the low emission burners at 0.3 and below. There are some areas around the country that do have 0.7 regulations, and obviously there's incentive to get to that. But the industry as a whole is, while not necessarily incentivized for any particular reason to go lower, they are always pushing those numbers lower. And if you were to look at the emission levels over time, you would see that over that same period, those emission levels have been reducing down from, that 1.5, 1 gram mark to very consistently below 0.5 now. And efficiency is has a benefit directly to the customer, because obviously that relates directly to value for money in terms of heat use. So that is really the number that the customers, the end users, would care about the most, because that's money for them. Yeah.
I've got a supplementary question, if I may. The test method, Richard, you qualify for the National Language Standards, or you can using the ASNZ 413 413.
Yep.
And it's a benchmark, but in reality, do you think it's a good way of testing things when we're trying to achieve in the real world reductions?
Well, I think that with those test methods, they were never set out to represent real life. They were designed to be a repeatable test method for the industry to use as a consistent sort of benchmark to test against. There is a lot of data to show that while they may not be 100% representative of real life testing, fires that do meet and exceed those regulations are significantly cleaner in real life compared to older technology that doesn't meet that. Does that answer your question, Jeff? Yeah.
We've just got one online question, which may be one for you, Richard, or maybe someone else in the audience, perhaps. And that was simply, what is the current population or proportion of LEDs in the population in New Zealand? Does anyone know? Richard, do you know?
I don't have that in front of me, no, but there might be somebody better qualified to answer that there.
Would anyone like to hazard a guess on that one, an educated guess? Maybe we'll come back to that one. I will mention that the hopefully all going well technology has worked. A recording of this event will be online, and also people will be able to post questions on the online forum, and our speakers will be able to respond to those. At this point, however, do I need to do anything on the screen? No. Okay, so I'm going to hand over at this point to Dr. Wayne Webley of ARS Limited, and hopefully we can bring his. There we go. This is yours, isn't it? No, that's yours. Okay, just one moment. It was that one, wasn't it? Presentation. Yeah. And just how do I advance the slide? Just 1 second before you do that.
Sorry, first.
Let's move this slide.
No, sorry.
That's pointer slide change event. All right. So the right hand one's to move forward. Yeah.
I'm the change, sorry.
Yeah, so you can start there.
Start. Ready to go?
Yep. Okay. I wasn't entirely sure how to pitch this or where to pitch it, so I've come up with some ideas which are hopefully provocative and informative about where you might go from where we are now with low emissions burners if you lived in an ideal world.
Sorry, sir.
Oh, okay.
Thank you.
So I wanted to think about what an ideal wood burner would look like. What would we really be aiming for? It would be really great if there were no particulate emissions. Obviously, if you burn wood, it's going to emit carbon dioxide, water vapour, and hopefully nothing else. And my thought really is that there's no real reason why you can't produce a wood burner with no particulate emissions. It would be really nice if it had 100% efficiency. That is, every bit of energy from the wood could actually be used to heat the room. It would be nice if it produced a really even temperature. You put on an electric heater, you just get a nice even heat. If you put on a gas heater, you get a nice even heat. With most wood burners, you put a load of wood on the fire, and the room gets hot and hotter, and then it cools off as that load goes away, and so the heat goes up and down. And it'd be really nice if you could just operate it from the comfort of your sofa. We're so used to doing that with everything else, why not a wood burner?
So that's my thoughts just as to where we might start. And I wanted to talk a little bit about the underlying theory of wood burners and how that might inform how we might approach actually producing an ideal wood burner. So I started off with zero particulate emissions. And we're thinking now about what do we need to drive the combustion to completion so that there's nothing left in those flue gases except carbon dioxide and water. And it's pretty simple. In a lot of ways, this stuff is not rocket science. It's pretty simple. You need enough oxygen. Basically, you're combining fuel with oxygen to produce carbon dioxide and water. And you need the 3 T's. You need enough time for the reactions to go to completion. The higher the temperature, the faster the reactions go. And you need enough mixing and turbulence so that the fuel gases and the oxygen are well mixed. And with those things, you can drive the reaction to completion and you can have zero particulates in what's going up the flue. One of the key things, though, is that has to happen right throughout the burn cycle. So one of the problems with a lot of the burners, for example, at startup, or when you reload fuel, the firebox gets cold, things get out of kilter, and you suddenly produce lots of emissions. So a lot of burners have an optimum or a sweet spot, and when they're operating there, everything's pretty good. But if you're away from that for any reason, if your operator does something bad, you suddenly start to produce emissions. So your ideal burner basically is able to have ideal conditions all the time. So let's just think very quickly about wood combustion. And I've basically divided it into what I've called primary combustion and secondary combustion. And the terminology changes a little bit on where you're reading, so I'll talk about what that means. So when I'm talking about primary combustion, I'm thinking about what happens to the actual logs of wood. Those are the primary thing that burns. And there are a couple of phases to that burn cycle. You put the wood in there and it starts to heat up and volatiles are driven off. So those volatiles consist of the moisture in the wood. And then there are chemical reactions that produce gases that are evolved from the wood and tend to burn in the flames above the wood. So they're gas phase reactions. And when those are completed, what's left is charcoal. And that charcoal actually burns by a different process. So it's a surface combustion. Air has to physically come down onto that charcoal. It has to be hot enough so that charcoal glows and burns. So in order to get the volatilization under control, you need to be able to control the temperature in that primary combustion zone. When the volatilization is complete, then you actually need to be able to control the temperature and deliver enough air to keep that glowing combustion of the char. If you don't, you start to produce carbon monoxide rather than carbon dioxide. You don't really want that either. So basically, just to reiterate, you want to be able to control the temperature in the primary combustion area and the oxygen. And the key thing about this in the ideal burner is you're controlling 2 things. You're controlling temperature and you're controlling combustion. And that tells you a lot about what that ideal burner needs to look like. So the secondary combustion is what happens to the combustible gases. And they're just a complete hodgepodge of nasty chemicals that come off the wood into that secondary zone. And the secondary combustion is the process of burning those completely so there's nothing left. And I just wanted to talk a little bit about the technologies over the years. So essentially with the really old burners, there was no added technology to drive that secondary combustion. There was some flaming combustion that was really just driven by the heat from the embers. And a little bit of oxygen that came on the top. But a lot of the unburnt gases spilled over the top into the flues, and you got quite a lot of pollution. So the LEBs, the low emissions burners, basically the technology was to introduce air bars or secondary air, and you can see that in this picture. I'm going to walk away from the microphone for a moment. Basically what you come across here is air, what they call it secondary air, is introduced. And you can see there's a really vigorous secondary combustion up there where that air, and it's usually preheated air, is being jetted into the unburned fuel gases and creating secondary combustion. But you can also get the sense that although that's actually really helping, what happens to those gases beyond there is they flow up typically over a top baffle plate where they cool and then on into the flue. And so there's still quite a lot of potential for unburned material to flood out into the atmosphere. And then we talk about the current crop of what are called ultra low emissions burners. So these are the ones that are currently being allowed into Christchurch. And what they've done there is the top chamber is where the wood is. That's where the primary combustion is happening. And the unburned fuel gases, there's some combustion obviously in the gas phase going on there, but they're being sucked down through the ember bed into that bottom chamber. And that bottom chamber is just burning gases. So what they've done is they've created a secondary combustion chamber, but there is no control really over that. So basically the temperature and the oxygen levels in there vary through the burn cycle. And although it improves things a lot, and it's, I think, a lot more tolerant to mishandling by the user, at the end of the day, if the conditions are not right in that bottom chamber, the stuff floods over into the flue. So in the ideal burner, we'd have the secondary combustion chamber, but we'd have it held at an optimum temperature. If it's too cold, there isn't enough temperature there to drive the combustion to completion. But if it's too hot, you start to form nitrogen oxides and you create a whole lot of additional problems. So we don't want it too hot either. There's got to be adequate oxygen in there, and there's got to be optimum mixing. There's got to be really good turbulence. So this kind of points to where the technology might head. And this is just my view. As I said, it's a little bit provocative. I think we're looking at burners where there is really good sensor technology to measure what's going on. So measuring the temperature and the gas composition. There are ways to actually control those things. So some way to actually control the temperature, and that might be feeding some of the heat back, or it might be an additional heat source, like some electrical heating or some gas heating. I know people hate that concept, but I actually think that's not a bad way to go. And linking those sensors and the control of the air and the temperature is going to be some smart software. And I think that opens up just a whole range of really nice things that we really should be doing with wood burners. Some things you might see, hybrid technology like wood plus electricity or wood plus gas. You're likely to see combustion fans. So the difference, some heaters have fans now, but they just drive the air circulation around the outside of the firebox. A combustion fan is actually in the combustion path, controlling the flow of gases. Some controls on the air inlets to direct air to different places at different times. The use of high technology ceramics. And I think the designs of those combustion chambers would be optimized using things like computational fluid dynamics. So there's some potential there for some really nice research. None of this is new. It's really bringing things together that we know from other areas and applying them to what is at the moment a fairly basic technology. Let's talk briefly about what 100% efficiency means. So the first thing is that your combustion process, the burning of your wood to get carbon dioxide and water, actually goes to completion. So anything that goes up the flue that isn't carbon dioxide and water is actually potential energy that you haven't managed to release. So we talked already about what it means to bring that process to completion. So I want to focus on heat recovery. So basically anything, any hot or any heat in the gases, when they leave that flue, is also energy loss, energy that you could have used to heat the room. And my little diagram there came from a European website, so rather than dollars going up the flue, we've got euros. If we are going to bring the temperature of those flue gases right down to ambient, then the key is water. And I just want to talk briefly about where that water comes from. So we know there's some moisture in the wood. You know, wood that we burn is 16 to 20% moisture, and that comes from the sap. But it's also important to realise that the combustion process, the combustion of the cellulosic type materials, combining with oxygen in the air, also produces water as a function of the combustion. So there's two types of water there. And as you cool those flue gases down, that water is going to condense. It's just like the laboratory experiment you probably did at school, where you boiled something off, you ran it through a condenser, cooled them down, and you got droplets of water. So one of the reasons people don't do this at the moment is because they have to deal with water in the flue if they cool the flue gases too much. The other thing is that the heat in the flue gases creates a draft. It's actually what pulls the gases through the combustion system. So in the ideal heater, we have a condensing system. It's going to deal with the water that's condensed, and it's going to involve some kind of heat exchanger to pull that heat out. So it might be a water coil, or it might be an air coil, but we're going to pull out that energy. But one of the really cool things about that is that there is energy in that water. So if you think about a kettle, you put energy in to turn the water into water vapor. The opposite happens when you cool water vapor down. It releases that energy back. It releases it into the condensing system. And that is a huge gain. The best that you can achieve without doing this is about an 80% efficiency. You've got a 20% gain in efficiency if you can do a condensing system. These are done overseas on large-scale boiling systems. They're standard. There's no reason why we can't apply them, particularly to low emissions burners. And as I've already mentioned, if you don't have a flue draft from the temperature, you're going to have to put a combustion fan in there. Okay, so just really quickly, what I've tried to do is say, if we're going to improve things, here's some of the things that I think we need to put into place. We're going to have sensors. We're going to have control of temperatures, probably using some kind of hybrid heating. We're going to have control of air using air controls. We're going to have combustion fans. We're going to have condensing systems, and we're going to have some kind of smart control that really looks after the whole thing. And there are some other benefits of smart control. So if you're actually controlling the combustion process, suddenly you can make sure that the heat is even. You can actually do what most heaters do, and that's actually sense the room temperature and control the output. So you can decide what temperature you want in the room, and your smart control will deliver that, and you can have your remote control. You might also see some automatic ignition systems. I mean, wouldn't it be nice if you're heading home and you could push a button on your cell phone and the fire would be lit? You'd come home, everything would be nice and warm. Pretty much like I can do with my heat pump. I can actually turn my heat pump on before I leave Auckland, so the house is warm by the time I arrive back in Nelson. You'll see web interfaces and you'll see smartphone apps. There's just a whole lot of cool things that you can do, as well as getting 100% efficiency and really clean burning. That's my presentation.
Thanks very much, Wayne.
Right. At this point, we're going to crack right on. So I'm now going to introduce Dr. Renee Haberle. I hope I pronounced that reasonably accurately. I'm very happy to say that the technology generally does seem to be working, because we're getting quite a lot of online questions, which we'll come back to later on. But for now, and make sure, have I got the right one? That's the right one, isn't it? Okay, why is that not coming up? Why is that not responding? That should work. Oh, it's just not coming up on there. Mysteries of technology.
Technology, you see. Yes.
Yeah.
Sorry. It has. Oh, that's because you've got so many PowerPoints open. That's why you can't see the final one. Yeah. And you're comfortable with the remote?
Yeah, it's okay.
Awesome.
Yeah,
Just make
yeah,
sure.
yeah. All right. Yeah, good morning, everybody. My name is Ryan Haverley. I'm the owner of the company Microsoft. And actually, I started this emission technology about 3.5 years ago because I saw the technology in Europe and I thought that's a good idea to clean up the air in New Zealand. And we're only talking about because at the moment you're not talking gases or all kinds, and that's how it goes. My company, I want to talk about electrostatic filters. That's my main talk, but I also involved in heat exchanger was mentioned for on industrial scale, where we can cool exhaust gas down and then condensate and take the energy back. And the other thing I'm also involved for 2.5 years now, I'm involved with the one fire, which is not a emission burner. The only one is mechanically fully automatic one, like the fire, you don't even have to close the door, close shuts himself, and here we go, and there's no manuals, no leaflets, nothing here. But I'm not going to talk about auto emission burner today. My topic is electrostatic filters. Electrostatic filters is a technology which has been years and years and years around for big plants, not small plants, like 20 megawatt. But we want to talk about EcoTubes. That has been developed from a Swiss company, startup company in 2008. They started with that appliance, which can be retrofitted on every single tube, in every single location, even concrete or whatever, and takes the emissions out. The results come with. I want to show you some pictures. But these guys have now 20 people involved, and 5 of them are only working on new technology, which is going to be here for the next 10 years. And I can't tell you everything because some of them are pretty secret. That's what they're doing too. Bigger models like 200 megawatt, that's the in Dunedin University. That's retrofit one. That one is washed or clean washed every 6 hours with water. That one is a module. That's an electrostatic filter too. 3 models, fully automatic, cleaned, dry, no water involved. That's the next step. And then we go up to 1.5 megawatts. But we're talking about EcoTubes. EcoTube, that's my house where I live. I put an EcoTube. I have an old campfire about 3 years ago, and I put that one up to get the things out. How does that work? Maybe you're familiar or not familiar with electrostatic filter things. You have a chimney here. The electric tube is up here. You put an electrode, and I brought something with me. It's an electrode. It's an electrode, and then you have actually the tube as such. That's the high voltage, which we actually transfer 240 volts, 30 volts to 30,000 kilowatt. And what they're doing, we're creating heat pumps. We're creating here an electrostatic field of 30,000 volts. And then what's happened, all these electrodes go up here and take the dust to the wall, and then they accumulate there. And we talk about dust in nanometers, which we don't say, and they go bigger and bigger. And pictures says a lot. I have for first some pictures and some tests which has been done in New Zealand, and when we was very first involved as well, and international tests. And maybe if you have time, we can go through a cost-benefit analysis, which can clean up the air and the health benefit of it. Well, that's a clean chimney. Just keep that in mind, clean chimney. As you can see, up here, that's the electrode. This goes down the chimney in the middle, center, and then we're going to do this electrostatic field. Just keep that in mind. The next one is a test we've done in Auckland, which has 22 kilos, I burned 22 kilos of fuel, no electrostatic filter. That's all the dust what they get after 22 kilos. Here, and I put his finger there, it's a very, very thin layer. That's all it is after 22 kilos burning. And that could start hot burn, and thing as well. Next one. That picture I took 14 minutes after start, and we burned 1.5 kilo of wood. And you can see here all the dust already there, the dust which is so small. After that small little thing, we have about 2 mil dust already there. After 1.5 kilo foot, that's what it takes it out. Another one after 2.5 hours, and you can see here, that's very important as well. You can see here small little crevasses in there, which what's happened here. Some of that dust which already collected either went fall down or went up in the air, which is called re-entrainment, and they are big chunks, and I'll show you afterwards. That's one after 14 kilos. 14 kilos, that's the dust which we collect after 14 kilos. I put up here and in here in at 1.6 meters. You see how much dust is there. It speaks for themselves. That's the re-entrainment, what they call. We talked about these clumps, which these small little flakes which can go up. The faster the velocities, the more of these big chunks go up into the air. But because they're so big, they don't affect your health, and they fall down roughly about the meter of the chimney. It's carbon. That's what's going there. That's when we finished, and you can see here. All that big chunk here, fall down, and it fall down when the person down there shut the door to reload. All of a sudden, everything went down back in the box on the back. That's the amount that he took out after finished, 22 grams. And now that's just to show you how much it is. That's not scientific or whatever. It's not. That's just to observe what's in the chimney we put out. That's nothing we can quantify. That's the big chunk. Shows the big chunk which came up here. The biggest one was 2.2 grams out of these nanometers, small little particles. Testing, that's a big problem. When we do testing with the tunnel dilution method, some of these flakes go up, go sucked in the tunnel dilution and hit the filter, and then afterwards you weigh the filter, and your test result is absolutely gone out. You cannot actually say yes or no, and you will see that in the results what they have done, and you can see negative actually efficiency. That's what's happened, and it's pretty big. That's about one day. I put about thing here that's about 2 mil high, and all in the middle one it's sparked with this filter. And when they hit that filter, they get weighed, they spread around, and they get weighed afterwards. And the result is that we have a negative result, which is it produces dust, which it doesn't. When we talk about method, we have different methods in New Zealand. We have a tunnel dilution method, as Wayne knows. Switzerland have different methods to Austria, but the big difference is, I'm not going through everything, is that the Swiss people and Austrian people counting particles in different ranges and different sizes. They do that with different methods, and that's a big difference. They don't only one. They're counting thing. You can see some of the disc is 15 different ranges. You know exactly how big they are. Now, what they've done so far, we started with Wayne back in 2014 with a big 28 kilowatt big multi-fuel burner from Reefton, the main outlet from Reefton. He fueled it up and we measured. And that was not really scientific. We just started and we see what's happening. And that was happening. That's your result. We can see we have, when we have a low burner, velocity is very, very little, we have up to 97% emission efficiency. If the velocity on 28 kilowatt burner is very high, the time spent in the electrostatic filter is very little, and therefore certain things goes up in the air. What we can do, actually, we could actually from a diameter from 150, we can go up to 200, which is going to use the velocity speed. And you can see here the red ones, it's negative stuff. Why they're coming comes only within training. That's how it works. And I'll show you another thing. That was back in 2014. That's just one little pictures. I love pictures because they tell the story. On the left-hand side, is filters without any rubber tubes, without a static filter. On the right hand side, that's we select the static filter. Then we have been approached from West Coast Council, Regional Council in the South Island, and I was concerned about that when we put these things up, these electrostatic filter up, we're going to have blockage because so much dust comes out. And then we monitored that every 2 weeks, and we went up there, had a picture, we measured the side, how much dust it was on the wall, and we see, and because it's not going to clog here, because in Reefton, they do the burners, they're big burners, multi-fuel, they slam them down in the evening, and they go 24 hours non-stop for about 120 days. And I really was concerned it's going to go. But to my really nice thing, it doesn't block, it actually cleans themselves. Everything falls down, but also because they're real big burners, it goes up here, these big blocks which I saw before, these big flakes, but they are not harmful anymore. It's after 6 weeks, and it looks like in a chimney. We've done one monitoring with only coal, and the other one was a 50% coal, 50% wood. Then we have approached to just measure once low emission burner, and we just took them from the shelf from 3 companies, and you can see the results. And we have like a startup, we use 10 together method once, startup, then two high burns, 2 low bores, and then we have the overall. And once again, you can see here in that one, minus 253 efficiency, means we have, where is that dust come from? It's only flakes which hit these filters and then actually affects the result. But overall, you can see you can see like here as well. That's the first one. That actually was a very nice one. That's actually at the end is coming out as an outdoor emission straight away. Just see. Then we go to international standards. The EcoTube has been tested in various sites in Europe, and I'm not going through, but you can see there are certain between 80 and 90%. There's one out there. The Swiss did actually what they've done. They tested the EcoTube for 2,000 hours without cleaning the EcoTube, without cleaning the chimney. And then you can see in the particles with 300 nanometers, we still have about after 92 days, 2,000 hours, we are way up there. Then also they measured the small one, the bigger particles between 0.3 and 3, and they're a bit lower, but they're still way up on the 80s, well up on the 80s as well. It's 2,000 hours without cleaning measured. Then the Austrians, they want to know that they need more, and what they have done, they set up a layer test, and they didn't use wood, they used pellets. And therefore they could actually use control the fuel, what is going to happen. And what they've done, they took the extremes. They took the extremes from oxygen high fuel, low and really high oxygen. And they have done 27 days of testing with 3 EcoTubes. And as you can see, that one, then the 49, and that comes back to again, comes to re-entrainment to flakes, which comes out. We have a really up a high efficiency, and they measure, as you can see, PM1 and PM8. Now that was the first stage. It took them 2 years to do so. The next stage was the following, and that's brand new from the press, really. And there's a scientific paper out there, which all the whole report is in German. They have done that to bring them to the field. And what they've done, they took 3 really old burners, put 1 EcoTube or 2 EcoTubes on, that's what they say, and the Ecosoft people developed one they call EcoTube inside. It's gas tight and actually can go into a house. And if that comes to the thing, they also put a way that you can fully automate mechanically, you can clean them if you want. It goes up to 60 kilowatt boiler. Now, it's pretty amazing, really. they've done two things. They have done 2 seasons, every season between 630 and 1,000 hours. And what they have done, every 10 seconds, they took a whole data collection out of it. It's an university. They have all the years and all the rest of it, and the manpower and everything. They just put PhD student on it, and they've done it. And that's the actual result. Unfortunately, I do not know what's really the raw gas is. But that came back on the reduction, and on that one it's bigger than 83, and on PM1 is bigger than 91 and 93. That's impressive for particulates in elements. And just as the end, because we have lots of air sheds, for the 1st of September 2016, we have a new law in place. Some of the airships are not allowed to have more than 3 exceedants. Some of them are really, really over the top. And nothing happened really. I'm not quite sure what these people, this council are doing next year, because they're going to fail it in. I don't talk about other emission, but that's a discussion we have to do. And I've done a small little calculation. That's nothing to do with scientists. I'm not a moralist. I'm not a statistic man. And I've took a small little and I put some figures together coming from headbands. How much cost, like a small little town in New Zealand, how much are the health, and they call them health and social costs. And these figures are coming from the March 2012 report, not from me. And I try to figure out something, how is an EcoTube is going to affect these figures. And I say, okay, we have a yearly cost for that thing, we have $11 million, not my figures once again. And we put that EcoTube on, and only the first 5 years, we're going to put 5% reduction of health costs. That's not much, just 5%. And then after 5 years, no more increase or reduction, just leave it like it was. And at the end, for that small little things, and if my figures are right, it's $35 million. And we can spend $4 million. Unfortunately, people with the money in hand don't see the real good things coming out of that. Conclusion, put your EcoTube back. It was very, very efficient. Very quickly, because small little towns, you could put 4, 5, 6, 7, 800 on a small little town and clean it. For instance, Alexandria, 920 chimneys. This summer, put one on, cost about $2.5 million. And we also look after these things. You're going to sweep the chimney, because that's not a mandatory thing in New Zealand. In Europe, it is. You have to sweep every year. And you look after the filter for 5 years. And if you have this contract into place, we're going to extend the warranty from 2 to 5 years. And this EcoTube has a life expectancy at least 10 years. And that doesn't mean we're going to exclude other emission burner or other technology comes to the market, but we can really react very quickly. That's about me. Thank you very much for your attention. If you have a question, thank you.
Excellent.
Probably when I look afterwards.
Thank you very much, Rene. Very good food for thought there. But at this point, just in order to keep to time, we're going to crack on, and I'm going to invite Jeff Blewett, formerly of this parish, now of Golder Associates, and see if I can find the right one. So which one? That was yours. Have I done the same thing? Usually not made it come up on the screen. We're okay?
Oh, you're not okay on that screen? You're okay here.
Okay. You right, Jeff? Yeah.
Good morning, everyone. Hey, thanks for the invite to the workshop. As Ian alluded to, 5 years ago, I left NIWA and went to Golder Associates, and my time at NIWA was very exciting because some of the projects I worked on was real-life emissions from domestic burners. And my time as a consultant, I've been really fortunate to do a lot of work with the ultra-low emission burners. So that's how I've ended up here today. So first of all, what is the definition of an ultra-low emission burner? Now, I will apologise here, and I have apologised in our presentation. I didn't coordinate with Wayne, so there's a little overlap between the two of us, so please forgive me for that. So the definition of ultra low emission burner is that 0.5 grams of TSP per kilogram of wood burn and an efficiency of 65%. And that compares to the NES compliant burner, which is 1.5 grams and 65% of efficiency. So there's two big differences there. One is the quantum of TSP allowed. The second thing is that it's also the test method that's applied to ULEBs. Now, I guess this is a Canterbury centric presentation here, because this is the definition that ECAN are using, and I believe it's similar to Nelson, but I'm pretty sure, because we don't have a national definition of ULEB, and that may be coming up, I don't know. Anyway, so that's what a ULEB is. Now, for those of you who, I'm just going to do a little bit of a combustion chemistry here, and apologies to Wayne here. So, for those of you on the internet, what I'm holding in front of me is about a 1.5 kilogram hunk of furnace radiator. It's a beautiful piece of firewood. Now, my 9-year-old son who's throughout the toilet humor would say, what's brown and woody? You know, and the implication then is a piece of wood, and this is what this is. But when I look at this, it's a beautifully engineered source of energy. It's a fuel tank full of volatiles you can burn. Once they've gone, you actually burn the container that's contained in. It's just fantastic engineering. And so let's put that in the context of the combustion chemistry. So just a 101, there's two little slides here. So taking you through the process, when you light a fire, the first thing you have to do is drop, there's about 20% moisture in that chunk of wood. And before you can burn it, you want to dry that off. Once that's happened, the heat in the flame dries off the volatiles from the wood, which are burned. Okay, and sorry, yeah. Once it's warm enough, the wood begins to decompose thermally, and that means the volatiles are driven off. What happens next is that at about 280 degrees, some of sorry, come on. Oh, so okay, it converts from solid to gases. The gases ignite at about 600 degrees. Now, one of my different terms we use here, I call it secondary combustion. Once those gases are released, you're left with the woody charcoal matrix, which is the charcoal. And at the end, when you get some oxygen on that begins to burn as well. So now this is important in the context of ULEBs, because as Richard showed earlier, in the LEBs, that combustion happens in one place. With the ULEBs, the engineers have been clever enough to separate those processes and provide conditions within which those two processes happen much more efficiently. So this is I've done some work on about 5 ULEBs. This is one chosen at random because it's some nice photographs. It's easy to find the parts. So the ULEBs, the most important thing is the way they're constructed. The first arrow points to the primary combustion chamber, and below that, secondary combustion chamber. Moving on to the photograph with the doors open. First thing is that those slots at the top, that's the primary air supply. And if you look carefully there, you can also see some second slots here. There's a secondary air supply. And between the thing, there's a little hole in the floor which the gases can pass through. Okay, so that's the general construction of a ULEB. Now there's various engineering variances on this, but the concept's pretty common to all the ULEBs on the market in New Zealand. So what I want to show you is how a ULEB works. What you're looking at now is a diagram with it looking straight at the ULEB. The top is the primary combustion chamber, the bottom is the secondary combustion chamber with a little hole between the floors between those two. So we'll stick in some kindling there. It begins to light up and boil away. What happens is the combustion gases escape through that little hole and head up the flue. And at this stage, what's happening is that the warm air rising in the flue is pulling air into that primary combustion chamber. Once things get hot enough, with the ULEB, we throw a barrier across the outlets to the primary combustion chamber. And at that point, what happens is that the air is then, due to the pull from the hot air going out the flue, the air is drawn into the secondary combustion chamber, and in this particular model, you can see it go up the sides of the combustion chamber, through the gap at the top, and continue up the flue. And at this point, what happens is we get that lovely, and I love the term, dragon's tongue in the secondary combustion chamber. So that's how a ULEB works. And so you're burning the charcoal at the top and the gases at the bottom. The conditions within each of those combustion chambers are designed to optimize but not perfect the combustion in the unit. So here's a picture of a ULEB operating. You can see the interesting things are the color difference between the top chamber and the bottom chamber. You can see bottom chamber is getting close to 1,000 degrees in those gases. The top chamber is more like 600. You can see the difference between the red glow and the yellow-white light. This is just a picture showing you at the end of the burn cycle. And it's interesting to have a look into the bottom chamber and see there's a little bit of ash in that secondary combustion chamber. Generally, instructions say you don't need to open that door to clean it out more than, say, once a month. You can see some normal ash collection at the top. So the emission testing, now this is a critical difference between LEBs and ULEBs. The NS requirement is to do the Australia New Zealand standard 401 4013, and that is, as Richard has said before, was simply always intended just as a comparison between burners. It wasn't necessarily meant to reflect real life emissions. What ECAN have done is they've developed a simulation of a real world emission test, and it's called the CM1 method, and I think they're up to version 1.4. And Wayne, from memory, you and Tim Mallett sat in the lab for weeks looking at this, trying to get the thing to go, and have developed something that isn't exactly real life, because of course you'll never get that, but it's certainly a better simulation than the standard method. And so, just highlight here that for that ECAN work, some of the burners were tested both to the CM1 method and the Australia New Zealand standard. And essentially, you'll see that it's not always the case, but the standard method is always lower than the Canterbury method. And that's understandable because the Canterbury method captures startup emissions, whereas the standard method doesn't. And generally, they're in order of about 2 of each other with the Australia New Zealand standard. And it's interesting to note, if you have a look at the standard method at 1.7 and compare that to the current NES requirement of 1.5, it's almost a tenth. That's pretty impressive. So just a little idea, so what does this mean in real life? So these calculations are not mine, they're taken directly from some ECAN documents. And essentially what we're showing here is the total daily emissions by type of burner. And clearly this isn't meant to be precise, it's indicative. So please just bear in that light. And I guess the thing I'd like you to focus on, we've got the standard test method. We do a little adjustment to that to reflect real life conditions. We've got a good approximation about how much wood's used each day, and we end up with a total daily emissions of grams per day. And you see that varies from 600 grams in open fires down to 21 grams per pellet burners. And the interesting thing there is that I guess just ask you to focus on the complying burners, because they're coming in about 63 grams per day. And just for anyone's interested, I'm at home, I'm in that bottom row. I've got a pellet burner, which is brilliant. I do about 63 steps, and I drag up a 15 bag of pellets every second or third day, depending on what time of winter it is. Great for heat, noisy as heck. You know, every heating system. My wife says to me, "Oh, can't you squeeze a ULEB, a discounted ULEB out of Renee?" So who knows, in the future we may have one for one of the other great ULEBs on the market. Anyway, please just look at that compliant burner, 63 grams per day. We do a similar calculation for ULEB. So the appliance was a 0.43 gram under CM1. Now, what we've done just to make it a relative test is we've added a safety factor of 50% to that. So we're using an emission factor of 0.65 and a wood use of about 18 kilograms a day. And that gives us about 12 grams per day for the appliance. Now you think back, the compliant burner was 60, so this is a fifth of the amount that a NES compliant burner would use. Now, look, once again, it's not precise, it's indicative. What I'm trying to illustrate is that there is a big step forward here with this technology. Now, there's an issue with this, improper operation. Now, all these ULEBs come with an information and operations manual, and you'll notice all of them have this is vital information. Store it with your passports and birth certificates, and but whatever you do, stick to the rules. But what happens is for the ULEB to work, you've got to engage the damper or the bypass, which blocks off the direct route from the primary combustion chamber to the flue. And it's great looking at these and seeing a variety of engineering solutions towards this. Rene mentioned that the Bionic has an automatic bimetallic strip that closes that for you no matter what you do. There's some can action door drives, so when your door closes the door, that goes across. Other manufacturers have put a temperature gauge on the flues, and the instructions say when you get to this temperature, close the thing. There's a red, green, white LED on a model that says when it's green, close the door. And there's one that says just watch your watch, and after this minute's time, close it. So, what happens if you don't close that thing? You've got it burning away, the gases go up there, through that aperture and up the flue, nothing else changes. You don't necessarily engage the secondary combustion chamber. And it's really interesting because some of them are designed so well that you get at least quite a little bit of secondary combustion chamber even before you engage it. But regardless, the question is, so if you don't close it, what happens? And intuitively, the emissions performance will be lower, the emissions will go up, so it's a bit confusing. Now, I tried very hard. There's actually a report out there that measures a ULEB in non-dangerous mode, but I couldn't get permission to produce that data. So I can say that they probably go up. I can't tell you how much or what was tested. I might do it for common drinks tonight, though. So the question is, but what does this mean for the management or the emissions from this? How much of the population doesn't use them correctly? And to be realistically, I guess I'm an optimist because I've got a whole drawer at home of manuals, check them every year, make sure I'm still doing stuff. But what is it really trying to do? I can answer that question, and I hope to get some comments about that later. So, this is my last slide, I think. So the management of ULEBs across New Zealand. So I got involved with ULEBs because in Canterbury, essentially the previous, what was it called? NRRP, the Natural Resources Management Plan, didn't allow any fires to be installed in new homes or homes without a burner. So what the retail and manufacturing people had to do is get a consent by which they created a capacity or an offset in the airshed that was sufficient for them to install them in new houses. And the way that was engineered, if I can use that word, was if you replaced a compliant burner, essentially you created an equivalent of enough airspace for 5 new ULEBs. But what we did was a bit of a trade-off. We said to Environment Canterbury, how about we replace one, we leave half the offset in the airshed for the benefit of the airshed, and we take up half the offset for new LEBs. So that's generally how the consents work for Canterbury. But with the recent Canterbury Air Plan, and it's a decision version, it's subject to appeal, and there are some appeals, but I didn't see any appeals on this particular rule. It's now, ULEBs are now a permitted activity within the airshed, so anyone can go and install one anywhere. And so, of course, I see Louise, you're thinking exactly, how does that work? Well, I'm sure the detail is essentially, I think you can only do a replacement install with a ULEB, and so as after 15 years those come out, that you can calculate there's enough headspace that we actually had enough improvement without necessarily forcing the consent forward any further. So Nelson had a similar role of permitted activity in some airsheds. I think they're most polluted airshed, is still prohibited for polluting the UN. Other reading question mark, and nationally, and place Rapunzel here, we might prompt her for a strategy on this later. Anyway, usually I think that's it for me. Am I over time? So thanks for your attention. Happy to take questions later.
Excellent. Thanks very much, Jeff. We are pretty much bang on time, so we're going to carry on. But this is our first time we're going to introduce a speaker from outside this office, hopefully from Germany, from Karlsruhe Institute of Technology. We should have Hans Power available.
Yes, I'm here. I'm here.
Excellent. We're just going to do a little bit of playing here to make sure we can see you on the screen here in Auckland.
Okay. I hope you have my presentation. Can you see the presentation, John?
We can see your PowerPoint now.
But we can't hear you quite well. Is there any way?
Okay, that's better.
Awesome.
Great. Thank you.
Okay,
Over to you, Hans.
So good morning and good night to New Zealand.
Sorry, just one moment, Hans. We haven't actually got you on the projector screens here.
Okay.
Just hold on one moment.
This is also not on the.
Is it working now?
Sorry, just a minute.
Okay.
Yep.
Don't want that. That's exactly what I want. Yep.
Okay, we're good. So we're going to now move up to slightly larger scale boilers, but hopefully something that's relevant for the smaller scale as well. So Hans, over to you.
Okay, so good morning and good night to New Zealand. My name is Hans Rudolf Power. I'm with the Karlsruhe Institute of Technology and one of the founders of Carola Clean Air. We have developed and constructed electrostatic precipitators for wood-fired boilers, and I'm going to report about the recent experience from field trials. We are cooperating with several manufacturers of wood-fired boilers in Germany, Austria, and Switzerland. Those are listed down here, and funding comes from the Federal Ministry of Environment and Commerce. So the wood combustion dilemma, I think, is well known in New Zealand, but it's also, of course, relevant in Germany. We have a great increase of renewable energies recently, but in general, biomass is the backbone of carbon dioxide neutral energies as it's used in traffic heat and electricity applications. Wood is a domestic and cheap fuel, and overall 78% of the renewable heat in Germany is supplied by solid biomass combustion. On the downside of all this is that wood combustion is responsible, in the state where I'm coming from, Baden-Württemberg, responsible for 95% of the domestic particle emissions. And of course, wood smoke contains ultrafine particles, which contain salts, black carbon, pHs, heavy metals, and those have been identified as toxic. So there's a good reason to do something about this, and several attempts to solve the wood smoke dilemma have been started during recent years. So in Germany, we have National Clean Air Ordinance, which requires 20 milligrams per cubic meters for boilers and 40 milligrams per cubic meters for stoves. Some cities in Germany and elsewhere start to regulate or even ban wood combustion in residential areas. And our approach is to improve the technology. We've heard already about improving combustion technology, of course, improving fuel quality and improving off-gas quality by filters is my topic. Just going slowly, going to the next slide. Okay, so we've heard already the tricks to reduce particle emissions from low emission burners. Similar technology applies to automatic boilers, which are in the range up to 1 megawatt in Germany. So primary, secondary, tertiary air, and to achieve optimum mixing to provide enough time for combustion and turbulence. This is the main idea. So our partner HTG Bavaria provides these boilers. Also others are in this field, and there's great success in this field. The second idea is, of course, to improve or to sort the fuel quality. So to use sort different qualities, premium quality, mixed quality, industrial and low quality. And those premium quality wood chips, that's what they are usually burning in these boilers, will be used for small boilers. Medium boilers will receive mixed qualities, and the industrial low quality will go to larger boilers which have a better flue gas cleaning. Okay, so let's summarize state of the art. Right now, the combustion technology in wood-fired boilers has reached a very high maturity. The particle emissions are mainly determined, because the remaining particle emissions are mainly determined by fuel quality, and to achieve ultra-low particle emissions for wood-fired boilers, the installation of precipitators is required, and for this we have developed the Carola precipitator. This one is shown here. In the Carola precipitator, the particles are charged by a corona discharge, similar to what has been shown previously by the Ökosolv group. And this charged particles are then deposited on stainless steel brushes, and the particles agglomerate there on these brushes, and by periodical turning of these brushes, particles will fall down into ash box. There they can be removed every 500 hours or so, depending on the fuel qualities. Of course, there are a large number of challenges for ESP development in wood combustion, and I don't want to run through all these challenges, but most of them have to do with variabilities of flow rates, operational parameters, variabilities of fuels, discontinuous operation, and of course, such a precipitator should be durable, corrosion resistant, has a low energy and resource requirement, and should be simple to use and have low maintenance cost. On the other hand, of course, it should not cost too much. So in order to achieve this, we have started long-term operation results with this Carola precipitator, which I showed previously in our test facility at Karlsruhe. And the main result is that the efficiency is in the range of 70 to 90%. So efficiency is always the red column here, depending, of course, on the inlet concentration. The facility is operated, cleans with off gas of 100 kilowatt wood chip boiler and we measure according to VDI 2066, and that's removal efficiencies in the range of 80%. So altogether, we were able to prove stable long-term operation of 2,500 hours with this setup. The main problem, of course, is that removal efficiency depends on power consumption of the precipitator, and an important aspect is to increase the power consumption up to a range of 30 to 40 kilowatts in order to get good removal efficiency between 70 and 90%. And then you can see, for instance, here in a 24-hour experiment, that the voltage is completely constant, and only every half hour the precipitator is cleaned and the voltage comes down for some seconds and goes up again. Same applies to current and also temperatures. So the trick is to clean the electrodes continuously by automatic device and to control high voltage by a high voltage microcontroller. Okay. We have also adapted this precipitator to a modern grate boiler together with our partner HDG Bavaria, and in this device, then the precipitator is included in the boiler, so it's integrated in the boiler, and all the precipitator functions are controlled by the boiler, and also even the ash removal system is integrated in the boiler. So tests are continuing, and looks very promising that this will become a product in the near future. Okay, so that's how it looks right now. No, let me continue. Okay, meanwhile, we have started our commercial operation at the Karula Clean Air company, and we have constructed precipitators for the size range from 25 up to 200 kilowatts. All of them are designed by computer-aided design, and quality control is established. We assemble small series of these precipitators and have delivered already several units to boiler manufacturers. Very important to sell, if you want to sell such a unit in Germany, you have to run through extensive performance tests by TÜV, and in order to get the certification in Germany by the German Institute of Bautechnik, and we have received these certifications beginning of 2016. We have also a certification in Switzerland. Okay, meanwhile, we have started to run field tests, and of course also some commercial units are already in operation. Also shows locations where the precipitator is in operation in Germany, in southern Germany, in Austria, in Switzerland, and altogether, as you can see, in most cases, the results are very promising. Most of the time, we achieve emissions below 10 milligrams per cubic meter and achieve the current standard. Yeah, especially interesting is this application to a pellet burner, which I will show in the next slides. So this shows one result of a 200 kilowatt boiler. So the inlet concentration is between 30 and 50 milligrams per cubic meter. Outlet concentration most of the time in the range of 10 milligrams or even below. So very good performance in this field tests. That's installation shown in Bavaria. Okay. So if you summarize the particle emissions of wood-fired boilers in test installation over the last 5 years or so. So in 2012, still classic wood-fired wood chip boilers had emissions between 20 and 100 milligrams. Pellet boilers were in the range of 30 to 20 milligrams. Meanwhile, modern wood chip boilers have reduced their emissions significantly, and by using electrostatic precipitators, then they come into a range between 10 to 20 milligrams for wood chip boilers and 1 to 5 milligrams for pellet boilers. So we are close to the emissions, particle emissions from oil and gas-fired boilers. Okay, so this is shown here for the ultra clean wood combustion, which we have started together with a Swiss company. The boiler 160 kilowatts, which includes a precipitator running at 20 kilowatts. Fuel is wood pellets, and upstream this boiler, very sophisticated boiler, has 10 to 11 milligrams, and downstream it may go down to 1 milligram with maximum 5 milligrams. So of course these highly sophisticated boilers have very small particles, so it's more difficult to precipitate them. Okay. Let me summarize. So we have collection efficiencies of about 80%. We reach the emission limit and have emissions lower than 20 milligrams. Meanwhile, almost 30,000 hours sorry, of long-term operation certification by German authorities, and the sale and production has started. Thank you.
Excellent. Thank you, Hans. I hope you're okay there. You sound like you're dying on that one. Okay, again, we're just ever so slightly behind time, so again, we're going to crack on, but this will be our final speaker coming up. So hopefully dialing in from Port Hedland in Western Australia, we have Olivia Johnson. Olivia, are you there?
Yes, I am.
Excellent. Are we able to bring Olivia up on screen from your machine, Yushi? I'll click on her photo.
Okay.
Excellent. Olivia, you appear to be on, or we can at least see you. If you bring up, how does she activate her slides?
Yes, I've got my. Let me share my screen.
Olivia.
Yeah, she's got it.
Excellent. We can see
my
slides, Olivia.
Excellent. Am I clear? Can you hear me clear enough? Or?
Is everyone happy? Okay.
Yeah,
Go ahead.
Okay. So hi everybody. My name's Olivia. I recently, about 2 years ago, did an honours project at the end of my university studies in Tasmania. And so this is what I'm presenting today, back to that study, which was aimed at reducing air pollution generated from wood smoke in a rural community in the north of the state, Perth. For those who aren't aware, Tasmania is in the southeast of Australia, it's the island state, but a relatively cold climate. And so wood burning is very popular in that place as well. The study was using a catalyst which is commercially available in Australia called SmartBurn. And there are no, before the study, there was no literature about whether SmartBurn does reduce pollution from domestic wood heaters. So it was the first study that actually quantified that effect. Before then, there was just some reports made by the manufacturer that it reduces particulate matter generated from individual wood heaters sort of in laboratory settings. So the data was very limited. And as you all know, that the wood smoke is harmful to health. So there's some respiratory and cardiovascular effects associated with exposure. And this study aimed at, or measured and aimed at reducing the PM 2.5, so the particles that fine particles, so up to 2.5 micrometer in diameter. This image shows a usual morning during winter in the Tamar Valley. So Tamar Valley is about 20 kilometres north of Perth, where my study was conducted. And Launceston, sort of driving into Launceston at the moment in this image. And so it shows what the morning looks like with the fog, temperature inversions, and the smoke being trapped beneath that inversion layer during the morning time. As I mentioned earlier, prior to my study being conducted, the only data was reports made from the manufacturer of SmartBurn, and they stated that the device reduces particulate emissions by up to 54% in single heaters in laboratory settings, so controlled conditions. There was also one field study done in Armidale, New South Wales, to test SmartBurn. It was tested again in single heaters, and it was a qualitative study. So it was actually measured by the size of smoke plumes generated from single heaters, rather than actually measuring emission concentrations in the air. The study was unique in that it actually quantified ambient pollution and determined the influence of SmartBurn upon it. The aim was to determine if SmartBurn influences ambient air quality, focusing on Perth, and also implies that the post-intervention pollution levels, or PM concentration levels, in Perth would be reduced compared to the pre-intervention winter and compared to control communities. So the pre-intervention winter was May to September in 2013, and then the post-intervention period was from July 1st to the end of September in 2014. So that was right after the study had been sort of rolled out in the community. This map shows, it's just a zoomed in shot of northern Tasmania around Launceston, which is the largest city in the north of the state. And I've pointed out here, so Perth circled at the bottom is actually where the study was carried out. And Longford, Hansden and Westbury were all used as the control towns to compare against Perth. But how the section was carried out can be divided into 4 steps. So the first stage was actually distributing the catalysts, the smart burn devices, to all wood heater houses of Perth. So this was done one weekend in June, where volunteers were on foot, door knocking and offering the catalyst for free for them to use in their wood heater for that winter period of 2014. The catalysts were actually donated from Smart Burn Australia, so they donated about 600 of them to us to carry this out. The second stage was the ambient air sampling. So the Environment Protection Authority of Tasmania has a blanket network, which is distribution of 29 fixed ambient air monitoring stations, looking like the image there on the right. And there's 29 locations of that throughout Tasmania. So they get data, hourly averages of particulate matter, so PM10 and PM2.5, as well as meteorological conditions in each town, so hourly averages of everything. PM10, PM2.5, average temperature, relative humidity, wind speed, and atmospheric pressure. So they gather this data every day, and it's available on their website as well for the public to see. So these stations were each in Perth, Longford, Hanson and Westbury, and so the data was actually used from each of these stations in order to analyse our results. The third stage was a participant survey carried out over telephone and email with people who accepted the device in June. So in September they were contacted and information was gathered to get an idea of those other conditions that weren't able to be controlled in the field. So such as those things that have been mentioned earlier that influence emission levels. So combustion conditions, the treatment and characteristics of the fuel they were burning, and how they actually operate their heater, the age of their heater, etc. So all those sort of other important factors that would influence the effect of smart burn and also the concentration of PM that we were getting from these stations. The final stage is the statistical analysis. Basically, how this was done to see if there was influence was to actually first a general additive model was conducted to eliminate any variation in PM2.5 concentrations that may have been attributed to the changes in weather conditions that were occurring every day and every hour. And then following that, the residual PM2.5 values for each town were then used to generate a general linear model, which determined if there was an interaction between intervention phase and location. So if there was actually a significant reduction to PM2.5 concentrations post-intervention, and especially in Perth, where the catalyst trial was actually conducted. This map of Perth shows sort of spots all of the houses that were, all the wood heater houses in the town that were targeted. The green spots are all of the wood heater houses that accepted a catalyst or a smart burn device in June 2014, and all the red dots are the houses, wood heater houses that did not accept the catalyst. And there are a few reasons for that. Either they said they don't actually use their wood heater anymore, they have electricity, or they didn't use their wood heater, or they weren't able to be approached. Either they weren't home the day that we needed the door knocking, and they didn't receive the postage afterwards, which allowed them to get to collect their catalyst at their local row house. For a few reasons, but almost 80% uptake was received for this study. The blue star is where the air monitoring station is situated in Perth. Okay, so the results show that there are some differences between each town in the mean PM2.5 concentration, but there was no significant decline during the intervention period, especially in Perth. we see there that the towns, while they are quite different to each other, there's nothing that shows that the catalyst trial in Perth actually caused a reduction to pollution. And there are various reasons for this. So the hypothesis was not, so the results don't support the hypothesis. There are many reasons for it. Perhaps the most polluting households weren't actually targeted by the study. So the 20% of houses that didn't actually receive a device and use a wood heater may have been contributing the most to the pollution in Perth, and perhaps they were, closer to the air monitoring station, and so they ended up sort of blocking out any effect that the intervention actually did have in the town. The participant survey did reveal that the canister treatment, as prescribed on the box of the product, weren't met by all participants. So on the SmartBurn device box, it actually states that the canister must be elevated and level in the firebox and kept away from direct heat. So there's a few special things that have to be achieved in order for it to work. And secondly, the combustion conditions, so the temperature of the fire, aeration. So how the catalyst actually works is, Joe probably should have explained earlier, is that it's a canister, steel canister with a solid mixture inside. And then when it's sat in the firebox and the heat from the fire actually vaporizes that solid mixture, and then it escapes out of the open end of the canister to act on the early byproducts of combustion and ultimately reducing the energy that's required to ignite soot and gases. And the firebox, and that is sort of claimed to actually clear the flue and clear the glass door of soot. But there are ideal conditions for that, so perhaps low, if the participants were actually operating the heaters quite low rate smouldering combustion. The temperatures of that may not have actually reached the threshold that's actually required to vaporize the mixture, so it might have been just sitting there dormant for most of the time that they were using the heater. And on the other side, perhaps if people were using their heaters on that fast rate setting, quite high temperatures, perhaps they would actually have vaporized the entire contents of the canister prior to the end of winter, so they're supposed to last about 3 months. But each of these things may have actually meant that the life of it was quite short, or it wasn't actually used completely at all. So the picture of the canister is well there on the side. This is that both ends are open, so they're going to solid mixture when it vaporizes and escapes out of those ends. And then finally, maybe the canister is actually insufficient for influencing community-wide pollution. So it's only ever been measured in the laboratory for single heaters and also in the field for single heaters. But this is the first day to actually quantify its influence community-wide, and it didn't find a significant difference between pre and post-intervention phases. So perhaps the conditions that were treated to the wood heaters in the laboratory weren't met in the field here. So I need to know what they are and if they can actually be achieved in the community. So, for example, how they, with the aeration and temperature and all those factors that influence combustion. The main conclusions. Firstly, the strength of the study, well, it had quite a high uptake. The participation rate was almost 80%. As the participation was quite high, but limitations are, like I've mentioned before, those conditions in the laboratory that might have been controlled, the types and the ages of wood heaters that were used, the airflow, and the rate of combustion settings that were actually used may not have been achieved in the community, which is why our results were quite different. There's no significant association between the catalyst trial occurring in Perth and the pollution that was actually measured in Perth. and also compared to the control communities was not significant. The catalyzed combustion in the community may be quite challenging to achieve with those special conditions that the smart burn canister itself requires and the specific combustion conditions that it requires in order to work as it's supposed to. So future research would be, would be useful in terms of determining what specific combustion conditions and fuel characteristics are required in order for members of the public and communities to be able to achieve what was achieved in the laboratory, and so that we can actually get the same results or similar results.
Great. Thank you very much, Olivia. Excellent. Very interesting results. So at this point, it's 5 to 12. Officially, we said we finish at 12, but we're happy to carry on. We're not going to throw anybody out. So at this point, hopefully, we can invite questions for any of our speakers and possibly see the sort of lunchtime discussion. Just before I invite specific questions, just a reminder that, as I say, we'll have our website, the WSRF website. We'll have a page dedicated to this meeting, and there's a place there where you can also post questions and our speakers can answer in their leisure. I have a couple of online questions, but first of all, I was just going to open it up to the room here in Auckland if anyone has a particular question they'd like to open with for any of the speakers. Go ahead. Oh, just one moment. I'll just close the microphone. So that everyone...
Also, if it is for one of the online speakers, if you mention the name, I'll bring them up on the screen.
This question is for Chief. With regard to the emission burners, you noted the primary air sources at the front of the burner. Is there a reason why you don't have concurrent flow from those types of burners?
That's a really good question, Michelle. So essentially, that wasn't all the detail of that particular design. There are a number of points of primary air, and the location and how they work varies from designer to designer. So the points taken, I didn't show that detail, but I think that is incorporated into some of the designs. Just I didn't illustrate it.
Any further questions? Okay, this one I'm going to ask if Richard, are you still there?
Yes, I'm still here.
So this is an online question. Why doesn't the industry lobby the Ministry for the Environment and/or the Minister to reduce the emission standard, particularly given your answer to Jeff?
I'm probably not qualified to necessarily answer that question. That may be a question better suited towards the New Zealand Home Heating Association as an industry body. So that's perhaps something they could answer at a later stage.
Does anyone else want to respond to that question? Okay, anybody else in the room with a question? Okay, I've got one more, an online question for Jeff. In your computed daily emission table, real-life emission factors, they don't include an estimate for the effect of improper operation, correct?
That's a good question. Essentially, the purpose of putting a correction factor into the standard test emissions factor, and we've effectively doubled that from what was measured in 401 to what we're using that calculation. So we think, ECAN thinks that adjustment would incorporate incorrect operation, maybe not at the extreme level when you're burning nippers and things, but I think my sense is that if you're looking for an adjustment, it's probably not a bad place to start and will account for most of the operation. Stand to be corrected though, even ECAN from here. It's just my interpretation.
Thanks, Jeff. Another question? Yep. Sorry, where's the microphone then?
So, Renee, with the retraining of the carbon, if you found that that's corrosive to roofs, and also has affected those sort of houses that have rainwater catchment, is there any effect on that?
Well, we haven't done any testing about the corrosion because we have high roofs on in New Zealand, and because it gets washed away and blown away by the wind, and we don't have data how it's going to affect the corrosion in 10 or 15 years time. And in the water, well, that's another question how many people are using wet water, but how many carbon in the air. And it has never been tested really. And for me, I think that's the lower the answer actually is that they're not the effects of the carbon on any rain in the physicians. You can know more about rain.
I'm a chemist now.
Oh, chemical, yeah, okay. But there was never an issue at the moment. I think there is going to be an issue now because it's going to blow away anyway. If they go on to dilute themselves as a car, of course there can be toxic stuff in texture as well. But the illusion of that one is maybe huge. Otherwise, you would like to water, you put gas masks on. I mean, that's never been tested, but it's I have to write into that when the water is 100% subsidized and fuel government. At the moment, and they are partly subsidized, it's basically partly subsidized.
Anybody else? Yes, we have one from Jeff.
Is it okay if I ask a question from someone in the audience?
Absolutely.
I think the intention it had been clearly sort of under consultation in pre-date. Can you give us any sense of a flavour of whether or not UAVs or post-combustion technology might be somehow incorporated in the upcoming revisions to the MES?
And you're quite welcome to come up to the lectern to answer that question.
That's great. So, thanks, Beth. As we were saying on our side, we are currently not in a position to sort of provide any greater detail on the review. What we can say at this point is that the review covers all the particular matter-related provisions in the standard, with particular regard to the recommendations made by the Parliamentary Commissioner for the Environment in terms of looking at 2025 and the duration, the averaging time. Apart from that, all the other related provisions would include the liquor standards. And so that's emissions and efficiency. And basically it would revolve around all those provisions, so it includes contracts and stuff.
Thank you. Again, one more chance for any further questions. In that case, I'll just make a final summarizing statement. I think we've heard today several examples where the technology of the burners themselves is there's clearly still some way to go. We've seen some directions. We've seen some promising technologies. We've had a little bit of a question about what are the economic market drivers to actually bring those technologies into our homes. We've seen that precipitation seems to be a promising technology. We've had a single study about a catalyst technology, which seemed to possibly be less promising. Now, obviously, that's not necessarily the end of the line for catalysts as well. And I'm sure that the manufacturers will come back and we'll hear more from that. Other than that, I'd like to thank all our speakers. I'd like to thank especially Ayushi and people behind the scenes here at NIWA to make sure the technology works. I mean, more or less, I think we got away with it. I think it works. Thank you all for coming here at Auckland. Thank you for everyone who's joined us online. And please check into our website later on and join in the discussion. At that, I'll say thanks very much and good evening.